Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss scalar multiplication of two-dimensional vectors. So, in this topic we will describe and define scalar multiplication of two-dimensional vectors. We will see how this can be used for change of units. We will also see how this can be used to record changes in locations over time. From this, we will deduce that the 2 norm gives us the speed of the object, and we will make some additional observations. Okay, given a vector u and a real number a, so here we see the two-dimensional vector u with entries u1 and u2, we will define the scalar multiple of u by a, and this is denoted by a times u, as a times the first entry of u and a times the second entry of u. That is, we are multiplying each entry of u by a. For example, if u is this vector 1.52, 7.91, then multiplying this vector by 0.5 gives us the result 0.76, 3.955. Also, multiplying this vector u by -2 gives us the vector -3.04, -15.82. Similarly, multiplying this vector here by 0.1 gives us a vector where each entry is multiplied by 0.1. Multiplying each entry in this given vector by -1.5 makes the first entry the positive value 794.715. The second value is now -67.635. So, consider the two vectors here, u and v. If I was to multiply each of these vectors by 0.75, that would essentially shorten those vectors by 25%. So here you can see the original vectors u and v and their scalar multiples by 0.75. Similarly, if you were to multiply both u and v by -1.2, this would make them 20% longer, but now they are stretched in the other direction. So u is in the first quadrant, -1.2u is now in the third quadrant. V is in the second quadrant, -1.2v is now in the fourth quadrant. Now, if a vector specifies a location, scalar multiple is useful for change of units. Suppose we have these two locations, and we know that these locations are relative to the origin given in meters. Now, because these are locations, I'm going to stop drawing arrows to them, because they are actually positions somewhere relative to the origin or the zero vector. Thus, multiplying by 3.28 gives us the relative locations of these 2 points in feet. So u now is just under 6 feet to the right of the zero vector and 1.3 feet up. Alternatively, v is almost 3 feet to the left of the zero vector and just a bit more than 3.5 feet up as well. Now, suppose that we have a vehicle and it's at this particular location relative to the zero vector. We're going to assume that this is in kilometers. Suppose that the vehicle is known to move in 1 hour 0.2 to the right, 0.3 kilometers up. Thus, after 1 hour, the vehicle will have moved up and to the right of the original location, ending up now at -1.6, -0.4. Question: where is the vehicle after half an hour? And more generally, where is the vehicle after S hours? Thus, if this vector tells us how far the vehicle has moved in 1 hour, then in half an hour, it would have moved 0.5 times this vector. So in other words, it would have moved 0.1 kilometer to the right, 0.15 kilometers up. Similarly, in S hours, multiplying the vector v by s tells us that it will move 0.2 times s kilometers to the right and 0.3 times s kilometers up. Thus, we can figure out where the vehicle's location is after half an hour. It's just the original location u plus 0.5 times v, which gives us the new location negative 1.7, negative 0.55. The vehicle's location after S hours can be calculated as follows. However, as we can see, this is now an algebraic vector. Let's take a look at this geometrically. Let us suppose that the location of the vehicle is given by the vector u, and its displacement per hour is given by the vector v. Thus, after half an hour, the location of the vehicle is now u plus 0.5 v, or just a little bit up and to the right of the current location of the vector u. We can tell that after 10 hours, the location of the vehicle will be given by u plus 10 times v, and that's going to end up at the location 0.2, 2.3. Also, at the same time, we can, given the current location, determine where the vehicle would have had to have been 3 hours ago to get to the current location if it was moving at that same displacement per hour for the past 3 hours. In this case, the vehicle would have had to have been at negative 2.4, negative 1.6 to get to the current location now. Also, here's one observation. If this vector tells us how far the vehicle has been displaced in 1 hour, 0.2 kilometers to the right, 0.3 kilometers up, then we can calculate the speed of the vehicle simply by taking the 2 norm of this vector. In this case, in order to move that far in 1 hour, the vehicle would have had to have been moving approximately 0.36 kilometers per hour. Now, we've already discussed displacement versus location. However, suppose we also know the change in acceleration in each dimension. So in this case, suppose that the acceleration vector is negative 0.1, 0.2 kilometers per hour squared. That means that in the x direction, in 1 hour, the velocity will have been reduced by 0.1 kilometers per hour, and in the y direction, the velocity will have increased by 0.2. Thus, if we know that the current velocity is 0.2, 0.3, then if this vector gives us the acceleration in 2 hours, the velocity or the displacement of the vehicle per hour will be entirely in the positive y direction with a value of 0.7 kilometers per hour. Now here's some nice properties about the real numbers. If x is any real number, then you do know that 0 times x is equal to 0 and 1 times x leaves x unchanged. Well, the same is true for vectors and scalar multiplication. If u is this vector, then observe that 0 times u is simply going to be 0 times each component, which is going to be the 0 vector. So 0 times any vector gives you the 0 vector. Similarly, if I multiply u by 1, well, I'm just multiplying each entry of u by 1, and that also leaves u unchanged. All right, here's a more challenging proof. The length of a times u is the absolute value of a times the 2 norm, or the length of u. Well, proof. A times u is just a times each of the entries of u. Now, if we use the definition of the 2 norm, the 2 norm of that vector is just the first entry all squared plus the second entry all squared, all square rooted. But wait a second, a times u1 all squared is just a1 squared u1 squared, and the same for the second entry in that sum. But wait a second, now we can factor out a common factor of a squared. All right, a squared is positive, and therefore we can state that the square root of a positive number times anything is the square root of that positive number times the other thing. But wait a second, the square root of a squared is just the absolute value of a, and the object that is being multiplied by is just the 2 norm of u. So for example, if u is this vector here, then observe that negative 3.5 times u is the vector negative 1.4, 1.05. Now, if we calculate the 2 norm of the scalar multiple of u, we get that that is equal to the square root 1.75. If we calculate the 2 norm of u and then multiply that by the absolute value of negative 3.5, we get that that is just 3.5 times 0.5, which is 1.75. Now, recall also from real numbers that x times y plus z is equal to x times y plus y times z. This just says that multiplication distributes over addition. So, for example, 6 times 2 plus 5 can be calculated by calculating 6 times 7, which is 42. Alternatively, we can calculate 6 times 2 plus 6 times 5, which is 12 plus 30, which is also equal to 42. You've also used this with polynomials. 3 times quantity x plus y is 3x plus 3y. Well, the same happens to be true for vectors. We're not going to prove this, but it's nice. It says that scalar multiplication also distributes over vector addition. So for example, if we have these 2 vectors here, u and v, if I was to multiply the sum by 0.6, I could add the 2 vectors together first to get that the sum of the 2 vectors is 0.9, 1.5. Multiplying that by 0.6 will then give me 0.54, 0.9. Alternatively, multiplying each of those vectors by 0.6 and then adding them gives us the result on the right-hand side. Summing those 2 vectors together gives us exactly the same result as we calculated in the first case. So therefore, this at least shows that, yes, it's reasonable to assume that scalar multiplication does distribute over vector addition, just like multiplication distributes over the addition of reals. Thus, in summary, in this topic we've described the scalar multiplication of a vector u by a scalar or real value a. Each entry of the vector is multiplied by the scalar a. This stretches or shrinks the vector, and if the scalar is negative, it will reflect the vector through the origin. This is useful for changes of units, as we saw converting meters to feet. If we know how much a vehicle is moving per hour, then we can determine where the vehicle will be at an arbitrary time. Similarly, we can determine the speed of the vehicle. From the speed, of course, we can also determine how far the vehicle has moved. We've also noticed that some of the properties of scalar multiplication are very similar to those of properties you already know about real numbers. So 0 times any vector gives us the 0 vector. 1 times a vector doesn't change that vector, and scalar multiplication distributes over vector addition. Also, we saw that scalar multiplication by a value a changes the 2 norm of that vector by the absolute value of a. Here are some references: Acknowledgments, the colophon, and a disclaimer. Cheers!